This is mine.
Oh, that's yours. Sorry.
No, yours over there.
Thank you.
Okay. Okay, so while we're preparing, I'll introduce our second speaker. It's a pleasure to have Diane Lambert from Google here. Diane is a statistician who has made a career in learning how to wrestle with and sometimes lame, tame data, not lame. She is now at Google, where she is a research scientist working on applications ranging from monitoring a gigantic robotic tape and to measuring effectiveness of advertisement and engagement at Google Apps. Her talk is statistics at Google scale.
Thanks, Pavlos, and thanks everyone for the invitation. It's hard to follow so many good talks, especially since mine is a bit misadvertised. So I called it statistics at Google scale, but it's really more like, why does Google need statistics? But it's really not good to have a talk out some place that asks why your employer needs you. So, so instead, it's statistics at Google scale. So let me tell you what my thinking about this is. So basically, statistics has always been a data-driven science. And that's because when there's been new data, statistics has advanced. So this is a picture of Rothamsted, which will be familiar to statisticians, or Rothamsted's familiar to statisticians, because that's where Fisher was. So Fisher arrived at Rothamsted in 1919, and they had collected much data over the years. They had been really careful about collecting data, but they had not been quite so forward-looking, you could say, about analyzing that data or extracting as much information out of it as you can. So, but Fisher, that was what he saw his role when he went there. And eventually he, in 1935, published The Design of Experiments, which is a book that's actually still read about why to experiment and how to experiment. So that was kind of the beginning of modern-day statistics, this need to analyze data from the field where the field really was a field. Okay? So now we come to Bell Labs, which will always have a, I'll always be fond for. But I wasn't here then, all right? I'm not quite that old. But this is Western Electric, all right? And that was Schuhart. No, that's not a picture of Schuhart, but that was sort of what switching looked like at that time. That was, computing at that time. And this again is, a pretty long time ago. I actually forget exactly when. But Schuhart had data on failures, okay? And again, this is data that people hadn't done very much with, but he thought about it and he came up with what are control charts, which are still used in industry at least, to monitor and to understand whether a system is in control, whether your levels of failures are increasing or it's just sort of you've got to expect a failure from time to time. But it was a whole new field that came about. We've already heard about Tukey. This is a picture of Tukey in World War II. He started off as a theoretical mathematician. He worked on topology, and in World War II, he worked in the munitions, which is testing, ballistics testing, basically. And struggling with the data then, he came up with his view that really visualization and exploring the data were at least as important as running hypothesis tests and everything else. But again, it was sort of looking at the data that people hadn't really treated seriously before that led him to advancing the field. Okay. Now, all these guys had, had the same big ideas, that you ought to collect data carefully. Their work was enabled by collecting data carefully, and they actually collected data carefully themselves. There's a famous story about Tukey. He lived in Princeton, and they wanted to do a traffic study. And so what he did is he sat out on the common at Princeton, and he himself recorded how many cars were passing, so that it could come before the before the town council. All these people took data collection very seriously. They all worried about experimentation, and they were all worried about uncertainty and bias. Knowing where your data comes from, people have already talked about that, that's incredibly important. Understanding, what problems you're going to have downstream because the data were collected in some way that you're not, that's critical to good analysis. And the other thing is you have to monitor all the time. So that's kind of the past. Those are the data that we had in the past, but this is the data that we have now. Okay. Basically, we can collect data from anywhere, right? We have sky surveys, which are gigantic. We have Mars data, right, which is newer sky survey data, if you'd like. We have maps data. We have medical data. Okay. We have blogs. We have Twitter. All right. People generate data to put on the web purposely, like in blogs. We have transportation data. We have all of this data. All right, and people aren't, it's just there. It's not kind of curated and collected in any way. And then we have Google, and what statistician wouldn't want to work for a company whose motto is, or mission is to organize the world's information and make it universally accessible and useful? I mean, if statistics had a marketing company, all right, we would come up with something as catchy as that instead of sort of what we're known for. But this is the world of today, okay? And this is, why do we need statistics today? Well, statistics is buried deep into Google and all search engines at this point. And PageRank was many years ago now, Google's new idea for search. So before Google, the way search was done was basically you took a web page, all right, and you analyzed it by looking at all the information on the page. And what Larry Page and Sergey Brin did was say, no, don't do it that way. What's important is not on the page, but who's pointing to that page. Okay, so if I have a blog and I point to the New York Times, that says nothing about me. If, on the other hand, New York Times points to me, all right, that says a lot about the quality of my page, because we all believe New York Times is a high-quality site. So basically, where you get the rank of a site, okay, is from what else links to that site. Now, of course, this is one signal among many now, but it's still in there. So this was considered a new idea, but it turns out that it's a very old statistics idea. This goes back to a paper that Kendall wrote in 1955 on paired comparisons. You have a list of like baseball teams, and which one's the best, okay? Well, if B is a high-ranked team and you beat A, that's going to push you up. If a lower-ranked team beats you, that pushes you down. It's exactly the same idea, and he had this whole thing in 1955, but he never got a patent on it, or his estate would be quite wealthy. So, at any rate, Google has a lot of data. Some of it is because users contribute data. Users put data through YouTube, right? A video is just data. Okay, there are a lot of data that's not necessarily contributed, but we have to record. So there are queries, results, and clicks. If you're an advertiser, we're going to charge you if you have a search result and somebody clicks on your ad. And then you're going to come back and say, who clicked on that ad? Not who is in personally, but how many people clicked on it? Where did they come from? Do they come from the US? Do they come from France? All right, and so we have to have all this logs data for things like that. There's a lot of logs data collected, obviously. And then there's lots of infrastructure type data. We do have a big network, so we have latencies and server loads and all the usual kinds of things. Power is the big thing, of course, that people are concerned about now. But then we also have experiments that generate data. So there's a lot of data. And the question is, does this mean we need a lot of statisticians? But the other question is, just what does this enable? So the old view was, if you had more and more computational power, you could solve problems that people couldn't solve before. So now, it's not so much that given more and more computational power, but it's given more and more data that you can solve previously unsolvable problems. Okay? So things that would be hard to do if you didn't have huge amounts of data become at least possible to do once you have huge amounts of data. So one example of this is machine translation. So you get text in one language, and you want to translate it to a different language. So what does this mean? Well, you have, you start off with the language G, and you want to go to the target language T. So you're saying, well, you've got this text. What's the probability of that translation in T, given what you started off with in G? So these are just, plain old probability computation. And they do this with what are called n-gram models, which are basically 3 words in a row or 5 words in a row. Okay. And you get all of these in one corpus, and then you have a translation of that corpus. So like court documents are translated often, for example. So you get translations of these, and you just sort of can match them up, okay? And now you've got a new document that you want to translate, and you just go to refer to this. So it's basically histograms, right? Because you just say, here I have T, and there I have G, and I've got this appears in this document, and, in so many other documents that are translated, I get this, I get a count of that. So how many times did T and G appear together? So it's kind of histograms plus some fancy smoothing that goes on. Okay, so suppose we take something like Arabic to English. So then we start off with what's called this BLUE score. And I always forget what BLUE stands for. But basically, higher is better. Okay? I'm sorry about that. But at any rate, what you can see is they started off, and you get up to, these are in billions of examples. And so the first on the left, those were things where they were actually translated by humans. So they're very carefully done. Okay, the translations are high quality, and you get BLUE scores that are kind of around 50-ish. Okay. And then you get up to about 5 billion examples. So now we've got a lot more examples, and you get kind of a big jump in the score. But it's sort of going up. It's sort of, roughly sort of linear up until 10 billion. And then at 18 billion and 237 billion, there are big jumps. And those jumps occur not because the models got any better, that there's a new tool, machine translation algorithm or something. It's got nothing to do with that. What happened is people started scraping web documents that were untranslated. So it's kind of like you're now using documents where you don't actually have the translation, or you have an uncurated one where just somebody has something up and then that somebody else translated it, but who knows who they were. It's just something you took off of the web. So it could be a good translation. It could be a first-year student's translation, which, it's not likely to be of such high quality. But even putting all this junk into the model, you still do better off with more data. More data has more power associated with it, not all the time, but quite often. If you have more data, you can solve harder problems. This is the listings of the most popular ways to spell Britney Spears in Google. And the only thing that's comforting is Britney Spears, some people do get it right, but some of the some of them are really, really clever. At any rate, this is how people do it. But still, when people type that in, whatever one of those they type in, they really want you to show Britney Spears and not some junk for somebody else that happens to have that mistyping. Okay? So if you have more data, you can start solving problems like that where people spell really badly. But you can even solve harder problems. And this is the one where, as you're typing, Google's returning results for you, right? So you type a few letters, and it's telling you what the results are. When it first started doing this, I found it highly annoying because I didn't like to be predicted that well. But I've sort of gotten used to the fact that I'm predictable. But as you're typing, all right, it is going to pull back data to find not only the results, but there's a completely separate work going on to find the ads that match your results and to try to generate diverse and better matching ads. All of that is occurring basically based on n-grams. So again, this is all the data on the web, and all of the data is buying you the ability to solve a problem that people couldn't solve before. I'm going to skip that. Okay, so, you know, if data buys you everything, do you really need science or do you just need data? Okay. Well, it turns out that data are not really enough. You still need to experiment because without experiments, you can't answer questions like, is this UI change better or is it going to confuse people? Okay, does this new code increase latency or not? The best way to do that is still with experiments. But now we're in, you know, everything can be productionized, as it's called, basically. So every query, if you've ever put a query into Google, all right, then you've been in an experiment. In fact, almost every query is in tens of experiments at the same time. Okay, and so these, I mean, basically at the same time, Google is running thousands of experiments at least. And these all start and stop at different times. They have different people in them. You could be a control in one experiment and in the test group in a different experiment. All right. And so basically, having a lot of data and having a lot of subjects gives you the ability to experiment in a scale that wasn't possible before. So experiments need statisticians. We all can believe that. That's what Fisher started us off on. But it's not true that they need experiments, they need statisticians for analysis. Because if anything is done in Google, it can only be done at Google scale if it can be productionized. If a statistician had to look at every experiment, experiments wouldn't be run. So what do you need statisticians for? You don't need them to do the analysis. You need them to design them. You need to have them design this, you know, how this can work, where you're starting and stopping them all at different times, and you're, you know, one person is at the end of one experiment and the beginning of another experiment both. Okay, the experiments overlap, but they're not simultaneously. How do you measure controls? How do you measure variability? Hundreds of metrics are monitored at the same time, so you've got the multi-testing thing. So basically, they have to design what the experiment infrastructure, if you'd like, is going to look at. Not in terms of what the computing is, but what actually this infrastructure is going to do. Even more than that, we design not experiments, well, they are experiments. We design the infrastructure that allows advertisers to run an experiment. So an advertiser wants to improve the rate at which people buy on their website. We will design an experiment, or they can push a button which will design an experiment and run it, because it's all JavaScript, right? Or something else that decides what goes on the advertiser's website. So again, statisticians are needed to design those kinds of experiments. Okay, so, sorry, going the wrong way. Skip that too. But not everything can be randomized. In fact, a lot can't be randomized. So suppose you develop a new tool that's supposed to help advertisers make better bids. So an advertiser, in order to set up an advertising campaign, has to decide what keywords they're going to bid on, which means if if they want to bid, if they want to have a campaign to sell their chemistry textbooks, then they have to decide what searches they want their chemistry textbook campaign to show on. And so in order to do that, they have to choose the keywords, they have to choose how much to bid, how much they'll pay if somebody clicks on it, all right? And they have to decide who they want to show it to. Do they want to show it just in the eastern US, for example? Do they just want to show it between 8 a.m. and 5 p.m.? That's probably not good if you're selling textbooks. But at any rate, they have to make all these choices, and some of them find it quite hard. So there are tools that people build to try to make this easier. So now you'd like to say, is this tool effective or not? So we can't, turns out, we can't really run an experiment here. We could randomly select advertisers to show this to, but they may or may not choose to use the tool. Okay? And if they use it, only some of them will use it right, and only some of it will use it consistently. Okay? So there is a selection bias here, because those who use it aren't necessarily like those who will use it in the future, because early adopters are always different. Okay, I only have a minute left, but I'm going to skip this. But what happens is, in many of these cases, when you have observational data, all right, then we're going to have what we think of as a parallel universe. So we have this advertiser who chose to do something, and they're going to have an outcome when this example doesn't fit these words, but I'll make it up anyhow. They're going to get an outcome if they choose to use the tool, and they're going to have another outcome if they don't choose to use the tool. But they're going to choose. We're not going to assign them to that. And we're never going to get to see the outcome in this parallel universe. So in this real universe, I chose to use the tool. But we'll never get to measure what my outcome would have been in the other universe. So we get this selection bias because we only get to see people in one universe. And if it were an experiment, a real experiment, we would put them in one universe or the other, and they wouldn't get to choose, so there'd be no, I choose the one that's best for me, and you choose the best one for you, and somehow we never get to see what I would have done in the other universe. Okay? So we get this selection bias, and there's, this brings you into the world of causal models. And they're challenging to analyze. Okay. So the only important point that I want to make here is we have to be able to run these at scale, but what's important here is being able to measure validity at scale. You can run all kinds of experiments, you can do all kinds of analyses, but it's not enough just to get the answers out. You have to be able to do automated validation, because you have to know when your analyses are not appropriate. And the automated validation part is actually very hard, and that's probably what's going to keep statisticians employed at Google for quite a while. At any rate, I think I'm out of time. Just some of the issues that do come up in Google where statisticians do work, I've listed here. Crowdsourcing is one that hasn't been talked about yet here. Maybe it'll come up later. But crowdsourcing is a big issue. That's, people just contribute their data. You don't know who's contributing. You don't know why they're contributing. All right? But somehow there's a lot of data out there, and you need to, Twitter is an example of crowdsourcing. And somehow you want to gather information for that. And that's a topic that has, it's kind of just beginning to ramp out, which is, again, something that will probably keep statisticians in business for a while. At any rate, thanks for listening. Finish?
We do have time for a few questions.
You talked of massive computational power solving problems, and then you said the use of massive amounts of data to solve previously unsolvable problems. I would just ask, why did you drop out of the second part of that, the massive computational aspects that are needed with the massive amounts of data now that n can equal all?
I didn't mean to drop it out. It's just that that's not, I benefit from that, but I don't contribute to that part of it. One of the things our table talked about at lunch, in fact, was how difficult it can be to work with data at scale, not just because it's large, but just because getting it back and forth can take time. Yeah.
Well, I have a question.
Ah,
So you show the mic is on. I go here. It's on. So you talk about Google Translate, and then at one point you said the quality. Is it possible you're actually picking up Google Translate? So you, is it possible you get translated pages that they've been translated by Google?
That's possible. That's quite possible.
All right.